Hi, this is John Mount from WinVector LLC. In this talk, I want to go over the exciting process of uncovering hidden price elasticity in a business process. What I mean by hidden is in realistic data, we tend to be dealing with mixed populations, such as website visitors that might be looking at our product and maybe if we put the right price can buy, and a mixture of website visitors that are maybe just clicking on our location to find the address. Maybe they've even already made a reservation, so they're not looking to buy at any price. We also get this for online shoppers and recipients of email marketing campaigns. We're going to drive this with an example. We're running a luxury soap brand and we email a coupon for a good deal on our soap to our loyal customers. We use a third-party emailer that doesn't supply open, non-open tracking, and that doesn't really solve it because people that open the mail may not be in the mood for soap at any price. So in addition to knowing whether they opened the email, we actually need to know intent. Some fraction of the recipients throw away the email unopened, are not fully considered even if they opened it. Some other fraction of recipients open the offer, remember our brand, and if the price is good enough, might buy some soap. So these are the price-sensitive subpopulation. We want to estimate the sensitivity of price or price elasticity of demand, which is how the amount of demand changes as we change the price of our offers. Here's our example data. It's a synthetic data, so we know what's right and wrong. The x-axis is the price we're offering. The vertical strokes are called a rug, and the histogram over them shows the prices we ran our price experiment at, where we sent out many offers at prices around 10 euros. Now, we don't know which customers even read our offer, but when we generated the data, we said that only 10% even consider the offer. And then they have this logistic style curve where more people take the offer at lower prices and fewer at higher prices. And because of these only 10% opening rate, this curve never exceeds 10%. Now the difficulty is if we use a standard method, no matter how sophisticated, that assumes there's only one population, we'll get a fit like this. This example is taken from logistic regression. What we get is a curve that says there's a sufficiently low price to get many, many people to buy. That is not what's happening, and it's often not what happens in the world. Now we overlay the actual generative model with this inferred model, and we see they somewhat agree in the region where we had data, but they strongly disagree at low prices. To avoid the problem, we could maybe just insist on better data. However, there's a lot of reasons we wouldn't get any of the better datas, like larger data, larger range of prices, more intermediate prices, and who opened or considered the stuff. The important issue is we may not be able to determine who considered our purchase because even though we may know if they opened the email, we don't know their intent. So you really do have to deal with this. Is the naive model that bad? It actually is. Now this is a new graph where, again, the x-axis is price, and now the y-axis is net revenue per offering. So that is the profit, assuming a €5 unit cost and a 5-cent marketing cost per email. At a price of 10 euros, we seem to get about 8 cents per offering. The naive method, its fit, says that the optimal price, the one that maximizes net revenue, is closer to 7 euros 10. And at that price, it predicts a €1.43 net revenue per offering. This is already a red flag, as this is not consistent with any previous experience of this business. And in fact, when we overlay the actual generative curve, the real price to net revenue curve, we get that the world would only generate 16 cents per offer at a price of 7.10. The real optimal is at a price of 8.90, where it would generate a net revenue of 31 cents per offer, or almost twice what the so-called optimized solution did. How do you fix this? Well, you can do some ad hoc things, like limit yourself to not too much of a price decrease or increase, but that means you have to run the experiment many more times, slowing down your business. Or you can do an ad hoc solution, a couple of which I've listed out here, which I don't really want to go over, but given that they're ad hoc, you're going to be debating whether they're correct or statistically efficient forever. We recommend a principled approach. Use Bayesian methods and a software package called Stan to model things. By model things, we just mean you draw out what you think the acceptance funnel of your market is, and then you use the computer to infer what that means the parameters must be. This works even in the presence of these multiple populations that are unmarked. We don't know which candidates are considering our offers and which ones are not. So we don't know what mixture we have of price-sensitive and price-insensitive prospects we have. What do I mean by write out the funnel or process? Well, here's one way to write it out on butcher paper. An offer, xi, starts on the left, and it goes to a decision node that it is either rejected or accepted with probability p. If it's rejected, it goes down the bottom rail to the unhappy outcome, no purchase. Or the offer is taken if it makes it past the first node in the second decision node with probability f of xi. And it's either not taken, maybe the person didn't like that price, or it is taken, they did like the price. Now the ambiguity is we only observe the incoming offer price, xi, and whether they hit the happy or unhappy outcome. We do not observe the path through the graph on what arcs they traversed. We translate this mechanically into Stan. This entire code block is essentially one if-else statement. On the if side, it detected they went to the happy state, which means they must have considered the offer healthily and liked the price. And we write down the probability of that. Then the failing state is just the other side of the if-else statement. Since the two paths are disjoint, the probability of either of them happening is the sum, so the ambiguity in the diagram of having two arrows we don't know which one we're on becomes the ambiguity of a sum where we don't know how much is from each contribution. And that's it. This is a very mechanical translation that we can teach and your teams can become familiar with. To repeat, we know xi, the price, and y, the total outcome, whether they purchased or not. We do not know the path taken through the diagram, we don't know the consideration probability, and we don't know how these populations value price. So those are the things Stan will estimate for us. If you can draw the diagram, Stan can complete the solution. How good is the Stan new fit? It's actually really good. This graph is a graph where price is the x-axis and probability of accepting or taking the offer is the y-axis. It has now been rescaled, so 0.1 is the top, not 1.0, and the purple dashed dotted is the new estimate, and the orange dashed line is the ground truth, or what's actually happening. And you can see the estimates are very close, only differing a little as we go back into the low prices. Stan correctly estimated the overall opening rate as 9.8%, which is very close to the actual 10%. It got the joke. Now, when we go to use this estimate, it picks a price of 892, which is very close to the optimal price of 89, and it predicts a revenue of 30 cents per offer cent for itself, and that actually turns out to be, it realizes 31 cents, essentially indistinguishable from the optimal solution for this data set. So what is Stan? Stan is free software that reasons about probability using samples. Think of this process as rigorous AI for numbers. Even in this day and age, not everything is text or language. There are numbers and physics you have to model. We can deliver solutions for your business problems or help your team add Stan to the repertoire. Normally Stan's used for scientific questions, so it can take a bit of a moment to get it working for business questions. Is this whole process easy? Essentially, yes. Once you get rid of inessential difficulties, it can be done very well. Stan can take a while to learn, and Bayesian reasoning is very off-putting for new users. However, it is something that we've successfully trained people again and again. Our group, WinVector LLC, has a success history in deploying analytics projects using Stan and other methods. We've done a lot of work on sales funnel estimation and optimization, which this was an abstraction of. We've got work on estimating uncapped demand from observed capped sales, i.e. when you have an inventory constraint, you might have more demand than you can sell, so that messes up your measurements. We have some really interesting stuff, which we've done for some clients on time series and estimating time series in the presence of recurring and non-recurring population mixtures. And we also have used Stan for a client in picking times of day for certain scheduling activities. We can talk with you about opportunities, help you bring Stan methods into your business, coach, train your teams, help assess your teams, or even do the contract and consulting work to deploy a new business effect at your business. Thank you very much for your time.